Shall we? Let me introduce you
Okay.
first. Welcome everyone to Bilecik Algebra and Number Theory Seminar. And next speaker is Professor Ben Kane from the University of Hong Kong, and he will speak about the bias conjecture for elliptic curves over finite fields and Hurwitz class numbers in arithmetic progressions. Thank you.
Okay, thank you for the introduction. Thanks for the invitation to speak. So if you know some of these terms, sorry if I repeat them. If you don't, I'll try to explain everything along the way, so hopefully everyone can be included. I'm just going to think of an elliptic curve in a really naive way. An elliptic curve is basically just this kind of equation, y squared equals f of x, where maybe f is a cubic polynomial with integer coefficients usually. This can be put into Weierstrass form of the form f of x is always in this shape, x cubed plus alpha x plus beta, and we'll denote that by e sub alpha beta. And for some ring, you can just look at the solutions, right? So you can just plug in which choices of x and y are solutions, very roughly speaking. So for example, you could take the real numbers and you could take solutions to y squared equals x cubed minus x. So this has solutions 0, 0, 1, 0, 2 square root of 6, 2 minus square root of 6, and so on in the real numbers. Okay. And as many of you probably know, there's a group law. In the real numbers, this group law comes from drawing a line, basically, between two solutions. And if you hit 2 points, because it's a cubic equation, you can always solve for the third solution. And there will be a third point that it hits, except for vertical lines, but that's kind of an exceptional case. Or double points from tangent lines. It's another exceptional case. But otherwise, it will always hit a third point, and then you sort of flip over to get a sort of interesting addition law, because a plus b coming back to itself is sort of not very interesting. Everything would repeat. The identity of this group is actually sort of a point at infinity, and this is well defined in projective space. So essentially, there's a well-defined infinite point, and you can sort of think of a vertical line. Every vertical line hits this point. Well, if we take, instead of something like the reals, if we take a finite field, then there's a finite number of solutions, simply because we have a finite set. There are finitely many x's, there are finitely many y's, and we can just simply count the number of solutions. And what you find is that the sort of expected value, so to say, of the number of solutions is p to the r plus 1. So where this field has p to the r elements. The plus 1 comes from the infinite point. And then there's a map called the Trace of Frobenius, which just takes every number to its pth power in this ring. And the trace of this across the elliptic curve, where you take points to their pth powers, has, well, it turns out to be related to the number of solutions in some sense. So the number of solutions is equal to p to the r plus 1 minus this trace of Frobenius. And Hasse actually showed that this trace of Frobenius is bounded by 2 times the square root of p to the r. So in some sense, compared to the expected value, it's sort of what you would take to be something like the variance. It's the size of the variance. So if we normalize, so if we take this trace and we divide by this sort of bound by Hasse, then we get a number between -1, because the absolute value is bounded by this number. So when we divide by it, we normalize, we get some number between -1 and 1. And the sort of interesting thing about this is now this number is always between -1 and 1, independent of p. So as we vary p, we can sort of ask a question, what values do we get? And so we can consider the distribution of this as you vary something. This is kind of the idea. Okay, so this leads to led to something called the Sato-Tate conjecture. This was independently found by both Sato and Tate. They can both conjectured this separately. So suppose we fix an elliptic curve over the rationals, and we fix two numbers a and b between -1 and 1. And then you can simply say, as x goes to infinity, what's the probability that this number is between a and b? This normalized trace, we know it's between -1 and 1. So we can ask, what's the chance that it's between a and b? So as we go across the primes or across the prime powers. So maybe here we fix, in this particular example, we fix the r and we vary the prime. So we take prime powers with a fixed r, and that would be this probability. Probability that it's between a and b for all the primes up to x is exactly this ratio. We divide by the number of primes and we take all the primes that have the property that we want. And what was conjectured by Sato and Tate independently is that this probability, as the number of primes up to x as x goes to infinity, converges to a continuous distribution that is an integral from a to b of this particular measure, which looks something like a semicircle. So 0, 1, -1, and it's exactly a semicircle. So the area under the curve is just the integral. And that's, this should converge to Harris, Shepard, Barron, Taylor. Perhaps others played an important role in this. This proof went through algebraic geometry. I'm not going to work in this direction, but I'm going to work on a related question. So I wanted to kind of introduce this and then say how what I'm looking at is a little bit different. So in their case, they fix an elliptic curve over the rationals, and then they vary the primes. Instead of doing that, alternatively, you could, for instance, first pick a prime power, and you could look across all of the, say, all of the elliptic curves over the finite field. So you fix the finite field, you average across all the primes, all the elliptic curves of that prime field, and you can ask the same question: what's the probability that this normalized trace between a and b? And well, there are, sorry, this should be p to the 2r. It should be p to the 2r. So there's p to the 2r possibilities because we have p to the r possibilities for x, we have p to the r possibilities for y, and then we simply go through and check all the possibilities. What's the probability that's in? So this is a similar sort of probability. It's not exactly the same question because we didn't descend down from a single elliptic curve, right? We sort of are going across all the elliptic curves, and we're not asking which elliptic curve are you reducing down to in some sense. So we're looking at the same objects because we're looking at the finite field. Those are the reduction of an elliptic over the rationals, but we haven't discussed a particular fixed curve. Well, as p goes to infinity, this probability converges to the same Sato-Tate measure. So we get the same distribution. So the probability that you're between a and b as you run through all the choices of alpha and beta. So he's really running through every single possible choice of elements of the finite field, looking at these elliptic curves. Now, some of these elliptic curves might be isomorphic, right? So he's saying, as I go across all the elliptic curves, morphic, this converges to the same measure. So we're looking at all the elliptic curves simultaneously for prime, and then we go across up with the primes. So we go across first, and then up with the primes. One of these is called vertical, one of the other one's horizontal. I remember which is called which. It depends on whether you turn this way. They have a proper name. I can't remember. I never remember which one is vertical, which one is horizontal. but this is one of the two versions. So I'm going to work more in this direction. So I'm not working in algebraic geometry. I'm going to work on I'll call it a simpler problem in some sense, a sort of on average Sato-Tate conjecture. So as I said, there's going to be some repeats. So there's some repeats under isomorphism, and there's also an equivalence relation under isogeny. So what is isogeny? Well, isogeny is basically finite morphisms which preserve the trace of Frobenius. So the isogeny class is all the things that have the same trace of Frobenius. And now I'm going to take a subset of the isomorphism classes. So instead of taking what Birch did, Birch took these elliptic curves E sub alpha beta. Instead of taking the E sub alpha beta, I'm going to run across equivalence classes. So I'm not going to do repeats for the equivalence classes, but I'm going to pick only some of the equivalence classes, some of the isomorphism classes. And I'm going to ask the same question. So of course, it's going to depend on how I pick my isomorphism classes. If I pick the one with the largest trace of Frobenius, then obviously it's going to be biased in that direction, right? So it's going to be some question of some property of my picking is independent of the distribution of these normalized traces or not. So am I picking in a biased way or not? And I'm going to ask the same question. Now, essentially, there's a sort of regular reason to normalize by the number of automorphs of the elliptic curve. So it has some symmetries. So we sort of divide out by the number of symmetries. We take a weighted measure, but basically it's a weighted average. So this is usually one. There's not too many of these automorphisms. So more or less, for most cases, it's one. So let's just say that this is basically just the probability. It's a slight weighting on the probability because it's sort of more convenient. And actually, if you look at Birch's original problem, it turns out that the number of repeats is closely related to this object. The number of automorphs is kind of built into his, although he's going across all of them, actually the number of times that they repeat is determined by this number of automorphs. So actually, it's the same question that he's looking at. If I take the set of all isomorphism classes, if I take all of them, I'll actually get the same as Birch. Okay. Any questions so far? So basically,
sorry, Ben. From time to time, we have some, I think, instability about your internet connection.
Yeah. Okay. Let me see. Let me try. Give me a second.
I don't know if you can fix it, but
yes, I also facing the problem.
Okay. Let me try. Give me a second. Is that more or less stable at the moment?
Sounds better.
Okay.
Now I can see you more clear in the video.
More clearly. Okay. Yeah, it sounds better.
Yeah.
Okay.
Thank you.
So I switched to a different Wi-Fi. Hopefully it'll be better now. Sorry about that. Okay.
No problem.
So so in Birch's case, he runs across all the elliptic curves where you vary the parameters alpha and beta. And in my case, I'm only going to look at isomorphism classes weighted by 1 over the number of automorphisms of the elliptic curve over the finite field. And it turns out that these questions are equivalent, actually. So if I take all of the elliptic curves, if I take the subset to be all the elliptic curves, then indeed I'm going to get exactly Birch's case. So I'm really looking at the same thing. The number of times they're repeated is determined by this weighting. Okay, so how am I picking The way I'm going to pick is I'm going to pick so that the trace of Frobenius, so the trace of Frobenius is an integer, right? So I'm going to pick so that the trace of Frobenius is congruent to some number m modulo m. So it's in fixed arithmetic progression. So I say take all the isomorphism classes over the finite field, where the trace of Frobenius is in some arithmetic progression, and then I'm going to normalize. So of course, after I normalize, it's no longer in an integer because I'm dividing by some square root of p thing. It's not even rational necessarily, but it's between when I normalize, it's between -1 and 1. And before I normalize, I look at the arithmetic progression. And the probability actually that a random elliptic curve is in this has this trace of Frobenius. This has been looked at by other people. But now the question is, how does the distribution vary as I vary the little m? So if you fix the capital M and you change the arithmetic progressions, you can ask what's the probability that that the normalized trace is what is the distribution of the normalized trace as the primes now go to infinity. So the arithmetic progression, we fix the arithmetic progression first, and then we vary the prime prime field, the prime power field. And it turns out the answer is the same. If you fix an arithmetic progression, then as the prime goes to infinity, the probability that the elliptic curves, which have that trace of Frobenius in the arithmetic progression, after we normalize, the probability that between A and B is again the same as the Sato-Tate distribution. So we get the same exact result. So it turns out that this, in other words, the distribution of the normalized traces is independent of the distribution of into arithmetic progressions, right? So there's an independence result, right? The probability is the same for the whole class of all of them or for this subset. So this is a sort of independence result, say.
Oh,
Okay.
excuse me.
Yeah.
So I see that it doesn't depend on m, but isn't it expected that when you sum over m, that should also match the original, like the total probability? So
yeah. So if you so you have to average though. Remember,
okay.
you sort of
Right.
yeah. So yeah. So it's like, what's the probability you're between here and here? But then you divide by more of them. So you divide by the size of E, right? So it's equal in each of them, and so when you average them, then you divide by m, and then it's the same.
All right,
so it repeats m
that
times,
makes
and then you
sense.
divide by m. Yeah.
Thank you.
Or you can think of it as you can think of it as a conditional probability, right? The conditional probability that's in this congruence class is this, and it's the same probability, which is the definition of independence. Yeah. Okay, so how do we prove this? Well, we use what's called the moment method, which says that a reasonable distribution is determined by its moments. So what are the moments? Well, these are the powers of the thing you're counting, basically. So if you run through all of the integer moments, all the integer powers of everything in this set E, so this E was our E sub m capital M. So we fix the arithmetic progression, we run across all of them, and we look at these moments. So we look at the kappa powers, and basically, if two distributions have the same moments, then they are the same distribution. This is essentially true, as long as the distribution is reasonable enough. So what we have to prove is that the distribution of these elements of our E matches the distribution of that integral. So in other words, what you can think of, so you might ask, why is this true? Why do the moments tell us everything? Well, in some sense, they sort of amplify all the different values, right? Because when you take the powers, if you get a lot of things close to 0, then when you take the power, you get something very small. So it will tell you sort of where it's higher and where it's lower in the distribution, right? So if you sort of think of it as a smooth thing, if you take it to powers, it will tell you how much weight is in that piece. So instead of looking at this distribution question, instead of thinking of it as a probabilistic question, we can think of it in terms of this equivalence question where we look at these traces to the kappa power. And I don't have to normalize because the normalization is just a fixed power of P. And I can ask, what's the asymptotic growth of this average, right? So the probabilistic question, when I look at the moments, becomes something about an asymptotic question of this sum. And the nice thing is we actually sum over all elements of the set E. So we sum over all the equivalence classes. So our question is, what's the probability we're in a certain region? But then to prove that, we only have to look at averages across everything. So this is sort of the convenience of the moment method. It allows us to look at kind of an average across everything. And as I said, you can sort of just pull out that 2p to the r over 2. You can pull that out, and you get that this is essentially the same sum, right? This moment on the right-hand side and the moment on the left-hand side are just varying by a power of p. So if we know the main asymptotic term, this will tell us the main asymptotic of the moment. And what did we do? Well, we computed the asymptotics of this. So as p goes to infinity, when we take the average that I just had from the previous one, and we divide by that power that occurred here, and then we divide by the number of elements in the set, that should give us a probability, right? So that should be exactly the probability. This S sub mm, that's the kappa equals 0 case. So the kappa equals 0 case will just be like a count, right, of the number of elements in the set. It's slightly weighted, right, because we have this 1 over this number of automorphs, but essentially it's just counting the number of elements in the set. So this ratio is exactly the probability we've been looking at in every single step, or the moment, the weighted moment essentially. And what we get is that this is the kth Kathrin number divided by 2 to the 2k if kappa is even, and plus an error term which goes to 0 as the prime goes to infinity. And if we go the other way, if we go for the odd kappa, then it's just the error term. It's just an error term of size p to the minus 1/2 this epsilon. So as p goes to infinity, that goes to 0. So to compare that, we look at that compared against the same question for the integral. And the integral, when you compute it for even moments, you get exactly that main term. And for odd moments, because it's symmetrical, you automatically get 0. Right? It's symmetrical around 0 because it's a semicircle. So the probability of the positive and the negative are going to cancel each other because it's an odd function, right? So when you multiply by -1, you get exactly the negative of that. So this will clearly be 0. And so indeed, these match. And that's how you prove the previous theorem. Okay, so after you've done that, you can then ask another question. So that's one theorem. Now you can ask, how does it converge to that term, right? So we had these sort of error terms. Yeah.
Sorry,
The
Ben.
question?
Yeah, there's a question of Igor on chat.
Oh, sorry. Oh, yeah. Okay. Let me see. Oh, I see it. Yeah. I guess the implied constants depend on m. Yeah. Yeah. The implied. Yes. The O terms in the error definitely depend on capital M. I think. I don't remember whether we determined that. I think that's partially answered by Castris and Kubrick's, because they determined this. So they determine the probability that you're in that set. And then I think we determine something like the main term somewhat explicitly. It might be more complicated than I'm thinking, though, because it's a little bit hard to determine. So here we're dividing by this S of M, capital M. And it turns out that there's a class number of an imaginary quadratic field showing up. So
Right.
it's possible that it might actually be ineffective. It probably is, because there's a lower bound that probably depends on the lower bound for the class numbers. And so that constant is probably not known, I guess. I think it's probably ineffective.
So you don't know
Yeah.
whether you can take, say, capital M to be a small power of P. It's not known.
Yeah, that I don't know. I don't know.
Okay, yeah.
We've only fixed capital M. Definitely not
Okay.
varying hybrid. We haven't done that. Yeah, that's
Okay.
true.
Thank you.
Yep.
Sorry.
Yep. Thanks. No. It's a good question. Yeah, I suspect it's probably ineffective actually. Yeah. So you can ask a question. How does it converge? So we know it converges because the error term goes to 0. Again, with capital M and little m fixed. But you can ask a question of how does it converge, in that you can sort of say, take away the main term and you consider the bias, the error term. So how big is the error term? Now, something of what I wrote down a moment ago says that that error term should be something like p to the minus 1/2 plus epsilon, or at least that's what we can prove. But you can ask the question, does this converge, for example? Does this difference converge or not? So what about the error term? So this is a question that's also been looked at when you look at elliptic curves over the rationals. So if you take a rational with a join t, so you take a function, you can ask the same kind of question. As I vary the parameter, so f sub t of x will be something like, x cubed minus tx or something like that. So to be some parameter that changes the actual elliptic curve that you're looking at. And it's a one parameter family. And you can look at the same question as you run t mod p, let's say, you know the main term. And it turns out that there's a sort of natural splitting where these c sub kappa j e's are all, they're all sums of things of absolute value, is what I'll say. So they have a kind of meaning that they really are things of a certain size, a power of prime p. So they're sort of bounded in absolute value by 1, and you're adding them up in some way. So they're not independent of p. I want to emphasize they're not independent of p, but they could be something like a character, right? So like, 3 over p or something like that. So as you vary the primes p, each one of them has absolute value 1, but if you average, you'll get 0, for example, if you take a character minus 3 over p or something like that. So, or here I take minus 1 over p, minus 4 over p, right? So, so as we vary the primes, we may have things that average to 0. So this was proven by Michel. And we can then say, take these things of absolute value 1, and for each one of them, take this limit. So this feels somewhat unnatural for a number theorist. Indeed, it felt very unnatural the first time I looked at it. Unnatural enough that I was confused about what they were doing. For each individual one, they're taking the average. But then if the limit is 0, they ignore it after that. So this has some geometric meaning for them. So Philippe Michel and some of his collaborators looked at these because they have a geometric meaning. These limits have a geometric meaning. So they were interested in these. What are the values of these? And when are they 0 and when are they not 0? And Stephen J. Miller, in his thesis, conjectured that actually the first j, the smallest j, which would be the first error term, where this average is not 0, is actually negative. He had some data, and this was somehow connected also to points of low height. So there's some sort of reason that he wanted this to be true. I don't know too much about that, but I know that he made this conjecture. And a number of cases have been proven. There are no known counterexamples, although there's some suspicion now that maybe the conjecture is only true when the original elliptic curve, the one parameter family, has low rank. In high rank, they're starting to suspect that it's actually false. But all of the cases they've looked at were of low rank, of course, because it's very hard to construct a high rank one parameter family of elliptic curves. So they don't really have any examples to check in high rank, but they have some reason to suspect this might be false. So that's that part of the story is actually very recent, within the last year or two. So originally up to that point, I think every example they looked at, they sort of suspected it was true. But then they started to see some data that they suspect maybe for large rank families it's false. Okay, so why am I interested in this? Well, if we reduce these elliptic curves to a finite field, so again, I'm starting at the bottom, right? I'm starting at the finite field. All the questions I looked at so far, I'm starting at the finite field bottom with this, and I'm looking at the question of sort of the average across the finite field, as opposed to fixing over the rationals and reducing. Well, if we fix this family here, then we get a set of elliptic curves over the finite field. Again, possibly with some repeats, right? So actually, they're taking the same kind of average that I'm taking, but they're varying in a different way. They're picking a parameter, and they're changing the elliptic curve based on that parameter. So they plug in every value of t modulo p, and for each one of them, they get an elliptic curve. And then what they're asking is, as I vary over this finite field, that set, so what is the sort of value of these things at absolute value 1? So I'm going to do the same thing with our construction. So I'm going to look at cases where we look at the elliptic curves in an arithmetic progression. So instead of starting at the top like they did over the rationals with the parameter, I'm just going to start with all the isomorphism classes, and I'm going to again fix that we're in a certain arithmetic progression for the trace of Frobenius. I'm going to ask the same question. We know now from the previous theorem that the main term is the Sato-Tate distribution. So what about these other terms? So we can ask the same question: is the bias, the first term where the limit is non-zero, is it positive or is it negative? So we can ask the same exact question that they asked, but we're asking over the finite field with this arithmetic progression instead of their setting. And we find actually that, well, we get an exact value for the second moment. So sorry, the conjecture of Stephen J. Miller is just for the second moment, actually. It's only the second moment. So we looked at the second moment in our setting, and we asked the question, what's the first value that's non-zero? And it turns out that it's usually the first one that shows up. It's almost always non-zero. And we actually evaluated it here. So this first evaluation, sorry, I think I've repeated the same thing twice here by accident. So we have this evaluation. So we have this evaluation. And so we can determine then when it's positive and when it's negative based on the evaluation. And and it turns out that it's positive infinitely often and negative infinitely often, we're going to see in a moment. So, sorry, this was, yeah. So it turns out it's actually, in our case, the bias is a positive density of the time positive and a positive density of the time negative, it turns out. So in our setting, it's very far from their conjecture. Of course, it doesn't tell anything about the conjecture because we started at the bottom. So somehow what this sort of says is the bias they're seeing is coming from the way they're choosing the elliptic curves at the bottom, because we're picking the elliptic curves in a different way based on this arithmetic progression. And in our setting, it's just random almost. Something like 44% of the time we get positive and 56% of the time we get negative or something like that. So we get a different bias than them. Now, we look at this whole setting, this whole story we look at in terms of class numbers. So up to now, I've talked about elliptic curves. But actually, it turns out that what I really studied, I mentioned a little bit when asked a question by Igor about the whether we can determine the constants. There's actually a class number showing up. And the reason is that the number of elliptic curves with trace T is related to the class number of an imaginary quadratic field, or not the field itself, actually suborders of the field. So it's the Hurwitz class number. So it turns out that because the number of elliptic curves with that trace is usually, I'll say usually because there's some bad isogeny classes, it's usually equal to this number h of 4 p to the r minus t squared, and then the trace is t for that isogeny class. So we just get t to the kappa. That was exactly, this s is summing over the t's to the power kappa, and the number of times that t shows up is the number of elliptic curves where the trace is equal to t. So we can use Schuf's work to conclude that essentially most of the time we get exactly this sum. So the sum of the elliptic curves that we're looking at turns out to be related to a sum of class numbers up to an error term, and that error term is just bad cases where Schuf's count doesn't exactly work. You get a slightly different answer. These are some exceptional cases like supersingular elliptic curves. So as I said, this h of d is a Hurwitz class number. It counts the number of binary quadratic forms, integral binary quadratic forms that are positive definite of discriminant d less than 0. So binary quadratic forms with discriminant d less than 0, weighted by the number of automorphs, 1 over the number of automorphs. So it's essentially, most of the time, these number of automorphs is 1, just as it was with the elliptic curves. So this is essentially just the number of binary quadratic forms of given discriminant up to isomorphism. Yeah, so this extra error term turns out to be kind of negligible. It doesn't have a main contribution to the asymptotics that we're interested in, either for the main term or the first error term. So it then remains to study this Hurwitz class number thing, the sum of Hurwitz class numbers with the t taken to a power. So now we want to change from looking at elliptic curves to looking at these Hurwitz class numbers, and this is actually where it moves into the realm that I'm able to attack. So the Hurwitz class numbers are really counting the number of binary quadratic forms, as I said, of discriminant d, weighted, but we don't necessarily have a GCD1. So this is the difference between Gauss's class number and this class number, is we don't have a GCD condition. And we weight by a half if it's the same as, if it's equivalent to this curve, but that automatically implies that the discriminant is minus 4 times the square. It's weighted by a third if it's if it's equivalent to this quadratic form, but then that's implies the discriminant is minus 3 times the square. So basically, other than these 2 special families, the number of automorphs is 1. So that you just divide by 2 or 3 in those special cases. So we had this t to the kappa showing up, and then we're subtracting a t squared. And so the way I'm going to view this is I'm going to view this as a series. And so I'm going to take this as a series of something with class numbers and a theta function. So a theta function, I'm going to look at a unary theta function, or one variable theta function, that's just exactly taking the t's that are in the certain congruence class that I'm looking at, the certain arithmetic regression. I take them to the kappa power, and then I take q to the t squared. So it's an expansion in q. Q is e to the 2 pi I z, so I take a Fourier expansion of this type. And then the generating function for the class numbers is exactly the sum of h of d, q to the d. And when I multiply them together, I get that the coefficient of q to the n is exactly the number that I'm looking at. This is this sum of Hurwitz class numbers. So the coefficient of q to the n is exactly when n is 4 times the prime power, it's exactly what I'm looking at in my on my former last page. So now I've moved the problem to investigating Fourier coefficients of this product.
Is it a modular form?
Yep.
Is it a modular form?
It's almost a modular form. it's nearly a mixed Mach modular form. It is a mixed. Sorry,
What about the weight?
The weight is 2. The weight is 2 plus kappa. So it's something like a weight 2 plus kappa modular object, I'll say. It's not a modular form, but it's a modular object. And
But
indeed, that is how I'm going to investigate. It's part of a non-holomorphic modular form.
I see. In sense of, is it similar sense of Eisenstein series of weight 2? Or this kind of
Yes.
almost?
So yes. So yeah, that's right. So it's a very similar to that. So there's 2 pieces, the H and the theta, and neither of them is quite a modular form. The H is missing a piece and the theta is missing a piece. The theta is missing a piece just like E2. The H is, yeah.
Sorry, some time difference in Zoom, sorry. What about analytic? Are they both analytic?
So these are both analytic, but when we add in the piece to make them modular, they're no longer added. So we can make them modular, but we lose holomorphicity.
I see.
And
thank you.
They don't have any poles at anywhere either after we add in. They have they're real analytics still. They're real analytic. They don't have any singularities after we add in the piece. It's the class number generating function is basically like an Eisenstein series, and the theta function is also kind of like an Eisenstein series for kappa equals 0, but then for higher it's sort of vanishes like a cusp form. Yeah, so indeed that's how I'm looking at it. Is exactly that question is leading into how I'm going to investigate this product. So as I said, this is almost a modular form. It's a derivative. It's actually a derivative of a modular form. So it's a quasi-modular form. If you take 0 here, it's actually a modular form of weight 1/2. If you take 1, it's actually a modular form of weight 3/2. But then if you have the higher powers, you've taken derivatives. So it's no longer a holomorphic modular form, it's a quasi-modular, which are like derivatives of modular forms. So this is exactly what you get. You get a quasi-modular form. And it's well known that quasi-modular forms, if you add in something like 1 over a power of y, some polynomial in 1 over a power of the imaginary part, times holomorphic functions, you can complete it to get a non-holomorphic modular form. So this is what we call a quasi-modular form, and it can be completed to an almost holomorphic modular form. So
So is it
Sure.
Q derivative or other derivative?
It's a Q derivative because when you take a Q derivative, you get a T squared out in front. So I took 1 where I take 0, and I took 1 where I took 1, so I have both mod 2. And then you take for the odd ones, you take the derivatives of theta 1, and for the even ones, you take the derivatives of theta 0.
And are there any Walsh-Bourget idea behind this? Or not related?
Okay. I don't think so. I don't know of any. I mean, they are Haffenberger weight modular objects, so they're going to get cusp forms. So in that perspective, yes. I mean, it's going to be related to coefficients of lifts, of their Schmurr lifts. They will have that relationship, but we're not viewing it from that perspective necessarily. Essentially, we just want to construct something modular.
Maybe it's a bad question. Sorry.
Oh no. It's fine. I guess some people here know lots about modular forms. Oh, a modular form essentially under this weight k slash operator, it goes back to itself. Classical ones are holomorphic and also have bounded growth towards the cusps. Half and over weight sort of have the same thing, but some kind of multiplier system is needed. Essentially, the problem is when you take the square root, you can't glue things together without a multiplier system because of branch cuts. So I like to view it just simply as a fixing of the branch cuts by this multiplier system, so that you can slash with two matrices, one and then the other, and slashing with the product is the same as slashing with the first and then the second, no matter which order you go in. So there's some consistency conditions that occur because of that. So these almost holomorphic modular forms, as I alluded to, are sort of a series in powers of the imaginary part to some negative power times some functions f sub j, where the f sub j are actually holomorphic. And these are also bounded towards the cusps, usually by assumption. And the f sub 0 term, the beginning term where you don't have the power of y, this is called a quasi-modular form. So those quasi-modular forms that we saw before are one of these objects. So if we add in all of these powers of y times some other holomorphic functions, then we actually get a really modular object. So we can construct a non-holomorphic modular form. So then what about the class number generating function? Well, actually, Zagier proved that the class number generating function is what we call a mock modular form. So that class number generating function, if you add in this non-holomorphic piece, then you actually get a weight 3/2 non-holomorphic modular form. So it behaves like a weight 3/2 modular form when you slash with the weight 3/2 operator, the slash operator. It behaves exactly like a weight 3/2 modular form on gamma 0 of 4. But you have to add this non-holomorphic piece. It might at first look strange, but actually it turns out later on it was realized that if you take a certain operator on this, you'll get the theta function, the standard theta function we saw earlier. You take it's like a certain solution to a differential equation for mapping to this, and it's related to the mass raising and lowering operators. So it's a harmonic object. So when you add a reasonable non-holomorphic piece, which in this case is explicit, this is the incomplete gamma function, then you get a non-holomorphic modular form. So you can complete the theta to some non-holomorphic object. You can complete the h to some non-holomorphic object, and then when you multiply them together, the weights just add together, and you get weight kappa plus 2. So this was Ilker asked this question earlier. This is the answer to Ilker's question. Here's the weight. So then the question is, what do we know about non-holomorphic modular forms? Well, there's something called an inner product on cusp forms, for example, where if you take two cusp forms f and g, you can integrate them against each other. F times g bar times the imaginary part to the k, dx dy over y squared. Well, essentially, the dx dy over y squared is an invariant measure. The f and g are modular of the same weight. So actually, if you sort of think of z and z bar as independent variables, then it turns out that you can take this as an integral of h mod gamma, because the modularity in z and the modularity in z bar add together, and the imaginary part has weight sort of -1, -1. It sort of has weight in z and z bar, and it cancels the other two parts. So that's why this is sort of well defined to take modulo the action of gamma, is because of this this property. So this turns out to be gamma invariant, then it's well defined. So you can ask a question about convergence. Well, if they're two cusp forms, it converges. It's positive definite on the space of cusp forms, but on the space of modular forms, it's not. It actually doesn't converge when you take an Eisenstein series against itself, unfortunately. So it does not extend to an inner product on that space, but sometimes you can take an Eisenstein series times a cusp form, and that actually will converge because it will decay enough for the integral to converge. But for the cusp forms, because it's positive definite, if you know the value, there's an orthonormal basis, right? Because it's positive definite, there's an orthonormal basis. So if you know the value against all the basis elements, you know which element of the space you have. It's a finite dimensional space. There's an orthonormal basis. So you can construct everything as a linear combination of the basis elements, and you just take the inner product and you know which form you have. So it's uniquely determined. So what Sturm said was, well, suppose I have a non-holomorphic modular form, and I integrate it against all the cusp forms. And suppose the value is well-defined. If the value is well-defined, then there's a unique cusp form that has the same values as that, right? So take an orthonormal basis, integrate your non-holomorphic modular form against all of them, then integrate another cusp form against all of them. If you get the same values, we'll say that's the sort of holomorphic version of our capital G. So suppose this inner product always exists, then there's a cusp form that has the same values. It's unique. Because it's positive definite, this is unique, because the values are determining the cusp form uniquely. So we'll call that a holomorphic projection. And he computed its Fourier coefficients. And it turns out later on, Gross and Zagier went backwards. They took the Fourier coefficients and wrote it as an integral. And they said, actually, if we take that as the definition, then we don't have to take the capital G to have modularity, because the integral is written previously only makes sense because H mod gamma, we're taking the action module again. We have to have F and G both have to be modular, right? Otherwise, the integral is not well defined. But Gross and Zagier's version, they took an integral to compute the coefficients, and they realized it was just a linear operator. It didn't require it to be modular. So they changed the definition. If you have something that is modular, their definition agrees, but if not, it's just a linear operator. So now they can split it into pieces. And so it preserves modularity. It's the identity on holomorphic functions. And essentially, because it's a linear operator, you can apply the operator to each of the pieces. So suppose we split some function that's modular into holomorphic. So this is modular, this is holomorphic, and this is other. So it's not modular and it's not holomorphic. But if I can compute the holomorphic projection on each of the pieces, then because it's a linear operator, I can compute all the things that I want. Now the left-hand side, if the left-hand side is something that the integral exists against it, then the holomorphic projection will be a cusp form, just as we said above, because Sturm's original definition will match. The middle piece, because the holomorphic projection is the identity on holomorphic functions, it does nothing. So we can solve, if we start with the holomorphic piece, which is exactly what we had the H times theta, we can rewrite F as the difference of the other two. This piece is going to be like a cusp form, and this piece is going to be something else that we have to compute. So the first piece is exactly, well, it usually converges. It doesn't always converge. So it's not quite a cusp form. It's actually a quasi-modular form. It's usually a cusp form. And you have to compute the remaining piece. Michael Mertens computed this for kappa even, and for kappa odd, it was computed by Ono, Saikia, and Saad. And so essentially it turns out this extra piece, this non-homomorphic piece that you add, the homomorphic projection of it, turns out to be something like an Eisenstein series, but with a weird condition that if you take the two divisors that multiply together to give n, it gets only the smaller divisors. So you don't sum over all the divisors like you would to some power. You only sum over the smaller divisors, something like this. And so we call this a kind of mock Eisenstein series. And it's, as I said, related to the sort of usual Eisenstein series. And it turns out the main term that's going to give us the main asymptotic is the main asymptotic is going to come from the Eisenstein series, the kappa equals 0 case. And the cuspidal part is bounded by a result of Deligne much smaller. And it turns out that this error term from this other Eisenstein series is also bounded by the same size as the Deline's bound. So essentially, when you put these together, you get that you get this sort of average. And the nice thing is actually that these things of absolute value 1, they're exactly when you take Deline's bound, you divide by Deline's bound, you get things of absolute value 1. Those are exactly the things for averaging. It turns out that those also satisfy asymptotic conjecture. So when we average them, because they're equally distributed, when we average them, we get 0. So it turns out we can ignore all Cuss forms when looking at this question. And these mock Eisenstein series give us some terms, and that's how we compute this, the first error term. And so then we show that sort of it's often positive and often negative. It's essentially just determined by some GCD condition. So if we're taking 2 times something less than 1 minus 2 GCD conditions, and when both GCD conditions are not satisfied, we ought to obviously have positive because we're subtracting 0. And when they're both negative, we obviously have negative because we're subtracting 2. And then we sort of found some conditions that tell us that we get a positive density of positives and a positive density of negatives. And so that's how we did this. So that's what I wanted to share today. Hope you enjoyed it. Thank you.
Thank you very much for this very interesting talk. So are there any questions or remarks?
I'm actually curious, like in the beginning, you showed this conjecture that the probability distribution goes to this integral over mu. Does that mu like depend on the shape of the elliptic curve? Or like how general is that?
So the mu is independent. It's the mu is just a semicircle.
Okay.
So the mu,
I see. So it doesn't depend on the elliptic
it doesn't depend
curve
on the
at
elliptic
all.
curve. That's right. Yeah.
I see.
Yeah. So it's sort of surprising. It's always this what they call the semicircular distribution,
Right.
or what's now called the Sato-Tate distribution. Yeah.
Thank you.
And it's also valid for the modular forms as well, because of the
That's right.
modularity conjecture.
Correct.
For the Hecke eigenforms, yes.
Correct. Yeah. For Hecke eigenforms, you have the same result. That's the coefficients of Hecke eigenforms when you normalize by Deline's bound.
Indeed. Yeah. More questions or remarks?
Can we come back for a second to the last slide with the conditions on positivity and negativity?
Yeah.
Yes.
This one? Yeah.
So what's the frequency of negative and positive values for a typical M? Is that 50-50?
So what we're able to prove is the number of positives is at least 13%, and the negatives is at least 25%. And we collected some data, and we got something like 44 and 56 is our guess.
So you don't believe in 50-50?
Not quite 50-50, unless it somehow equals out later on. But as far as we can tell, it doesn't seem to be. It's less. I mean, we could compute up. I think we computed the first million capital M's or something like that, and we got like 44% the one way and 56 the other.
This stabilizes, I guess, right?
Yeah, I don't know what these constant are. I don't know what 44%. I don't know. Yeah, I don't know what 44% is, but that's what we saw. It was just from data, basically. But my former PhD student computed pretty far because it's a really explicit calculation. I mean, you just have to take this product over all the primes dividing M, and then check two GCD conditions, and you check whether it's positive or negative. So for a given value, it's very easy, but it's a little bit complicated to determine for general, simply because if only one of the GCD conditions holds, then the question is whether this product is bigger or less than a half, and that's less obvious.
Okay. So if capital M is a prime number, then you subtract 2, and what's the main term? I can't figure out.
Yeah, so if M is a prime, then
this is satisfied, right?
Probably only one of the GCD conditions could be possible, I guess. If neither of them is possible, then it's automatically too big, but if it's a prime, I think we did a prime case. So you get something like 2 times 1 over 1 plus 1 over p, as long as, say, p, if m is not 0, let's say, if little m is not 0, then you get 2 times 1 over 1 plus 1 over p. And then you want to know whether that's bigger than 1 or not.
Okay.
So 2 over 1 plus 1 over p is usually bigger than 1, right? So then the answer is that it's positive, for example, for a prime.
Okay.
For capital M prime, the answer is just it's always positive, basically. Unfortunately, that's not a positive density of numbers, but for primes, the answer is easy. Yeah.
Okay. And sorry, just a question. This phi of m, is it the small m or capital M?
Oh, sorry, that should be capital M. 5 capital. Sorry,
Capital,
yeah.
yeah.
Cap
Okay.
Yeah.
That's what I
That's
thought.
right. Sorry.
Okay. Yep. Okay. Thank you.
Thank you.
Sorry, I was also going to ask like this percentage that you were saying. It's like I forgot the exact definition of this script A, but this percentage is supposed to be like the exact percentages. It's not like log weighted or things like that.
Right. It's like yeah, it's when you take the first error term after the main term of the second moment, it's for in the arithmetic progression. This is when you divide out by the power of p, this is exactly that number, basically. So like it's like p to the minus 1. So this 1 here is like p to the minus 1 times this is the second term in the arithmetic in the asymptotic expansion. So you look at the asymptotic expansion, the main term is that integral, and then the next term in there is this thing, the average of them. The average of those is this. So you average over all the primes from up to x, and then take x to infinity, and this is that limit. So it's like the p to the minus 1 term.
Getting, like, the exact bias.
The exact value. Yeah, that's right. The exact bias. We get a value for the bias in our setting. But then again, we don't know exactly when it's positive and exactly when it's negative, but you can compute this and figure it out for individual cases.
No, I think this is interesting enough. Thank you.
More questions or remarks? Thank you to the speaker again for this nice talk.
Okay, thank you.
And you have some thank you message on the chat, Ben. We are very happy to hosting you. Oh, there are some fancy things about Zoom is going on the screen. Yeah, this is very nice. And this was the November talk. And then for December talk, we will host Toshiki Matsusuka from Kyushu University. I think it will be second week on the December. We will announce them. So thank you again for this nice talk. And it is very nice. We have participants from different countries, from different time zones. It is midnight in Sydney and night in Japan, and also we have some participants from Russia and Turkey. It's very fun. I'm very happy about this, and the discussion is also very nice today. So thank you so much again, and see you next month, hopefully.
Thank you. Bye.
Bye-bye. Thank you, Bane.